So position vectors. I want to talk about dimensions really quick. Does anybody know what I mean when I say dimension? Like what's a dimension? How do you define a dimension? So any measurable quantity is a dimension. Within each dimension exist units. Okay? So we could make a box, and we could say this is the length dimension. And what would be in the length dimension as far as units go? Meter, inches, feet, light year. Anything that defines a distance would be in the length unit, right? What have we used so far in this class as far as vectors go? What kind of vectors have we been working with? Force, right? The dimension of force has units in it, and newtons is one of them. What's the other one? Pounds. You might see lbf, which is the same thing as lb. lb is pounds, lbf is pounds force. Well, pounds is a force, so those are the same thing. Those are two different dimensions, and we cannot mix those. We can't get any feet in our newtons, and we can't get any newtons in our feet. Okay? So what we're going to talk about now is a new type of vector. Now, vectors, we're going to treat it the same as other vectors, but it's no longer a force vector. It's a length vector, and we call that a position vector. You guys have learned about them before, so I'm just going to do a short introduction, because I think this is review. A position vector we normally use in this class, we use r. And a position vector simply locates a point in space. So if we wanted to locate, say, this point right here, point A, to locate that point in space, we could make a position vector that we would call r sub A. And that position vector would start at O, the origin, and it would go to A. Okay, help me fill this out in Cartesian vector notation then. If I'm standing at O, and I have to walk to A, but I'm only allowed to walk in the x, y, and z directions, how far would I go in the x? You have to pay attention to these little lines here. So I would go 4 in the x. Let me go ahead and draw that part. And then what would I do? 2 in the y, and then negative 6 in the z. That kind of blended in, but hopefully you get what I'm getting at. Okay? So if I had to walk from the origin to A, I would go 4I positive plus 2j minus 6k. And my units would be meters. Okay? So that's the position vector to get from the origin to A. Okay, so that's RA. Let's find RB. So RB goes from O to B. 6I minus 1j plus 4k. Any questions about those two? Okay, so we just defined two vectors. What we're trying to get to is we want to be able to find out what's the position vector from A to B. Let me go ahead and draw that in. The position vector from A to B, it looks like that. In this textbook, we would call it RAB. And I'd encourage you, when you write that in your paper, not to... The language that you use to yourself is important. It can help you learn. It can help you learn vocab. Don't call this RAB in your head. Call this the position from A to B. Position, when you see R, from the first one to the second one. So the position vector from A to B is what that is. How do we find that? Well, does anybody see... So we did vector addition, right? How do we do vector addition? There are two ways, either parallelogram or tip to tail. Okay, does anybody see a tip to tail relationship? What is a tip to tail relationship? Let's start with RA. RA plus the position from A to B equals RB. And this is something you got to get really careful with, is drawing your arrowheads and paying attention to them, right? The equation shown here is not RA plus RB equals RAB. It's not. This is a tail-to-tail relationship. This is a tip-to-tail relationship. So we have to do RA plus RAB equals RB. Okay? Then we want to solve for the position from A to B. We're going to say RAB equals RB minus RA. Okay, so now we can solve for that pretty easy. We're just going to say the position from A to B is equal to, we're going to subtract each component. Subtract the i's, subtract the j's, subtract the k's. We start with B and we subtract A. So it's going to be 6 minus 4i plus negative 1 minus 2j plus 4 minus negative 6. Do a little bit of arithmetic. 2i minus 3j plus 10k. Okay, so now I was able to find out the position vector from A to B by doing some simple vector algebra. That's one way to do it. A second way to do it is to picture yourself standing at A and walking to B, and only allow yourself to move along the x, y, and z axes. Okay? So we can actually get to that vector directly. So picture yourself at A, and you're walking to B. How far do you go in the x direction? We go 2. You can picture going out this way in the x direction, 2. How do I know it's 2? Because we started at 4, and then we moved an extra 2. How far do I go in the y direction? -3. That would look like this. And then in the z direction, we would go. So you can actually look directly at the diagram and get this from it. Picture yourself walking from one to the other. Which way do you use? It's up to you. You can always do either one. Most people will start off doing this one, and then as they get more used to visualizing 3D figures, they can start going to that one immediately. Okay? Up to you. Whichever one you're more comfortable with. Okay, the next topic is one that will never go away and will be in almost every problem you will do for the rest of this class. So it's important that you really understand it and really get to know it. Force directed along a line is what it's called. So what we have to figure out is how do we borrow the direction? How do we borrow the direction from the position vector? And that's what we're going to do right now. So I didn't give any values on this, so why don't I go ahead and just make some up. Let's say that B is at -2, 7, and 5. Okay, let's say B is at -2, 7, 5, and A is going to be at probably +2, 0, 3. But now we need to find the position vector from A to B. -2 minus 2i plus 7 minus 0 j plus 5 minus 3. Okay. And my units, well, I have to choose what the units are for this link. Let's say that those are all in inches. Okay, so I came up with a position vector. And you notice the force is directed along that position vector. So let's go ahead and write that in Cartesian vector notation. RAB is going to be equal to -4i plus 7j plus 2k. Okay, so now I have the full position vector. And let's just say the force is given. Let's say F equals 20 newtons. Notice there's no harpoon over that because it's just the scalar. Two pieces of information in this one vector. There's magnitude and direction. Okay? So if you had two pieces of information, let's say you had 5x, and you just wanted the x, what would you do? Divide out the 5. Okay, so that's what we're going to do. We're going to divide out the magnitude. So how do we find the magnitude? The magnitude of RAB is going to be equal to -4 squared plus 7 squared plus 2 squared, square rooted. And that's all going to be in inches. Okay, so our magnitude is square root of 69. And now I want to take out that magnitude from the vector. So the way I'm going to do that is I'm going to take the full vector, and I'm going to divide it by its magnitude. And once I do that, I'll have a vector with a magnitude of 1. What do we call a vector with a magnitude of 1? Unit vector. We'll call that UAB. And I'm going to put a hat over it, not a harpoon. A hat says I'm a vector and my magnitude is 1. So it's a stronger statement. Okay? So I've got my UAB is equal to the full vector over its magnitude. That's a very important equation that you'll use over and over again. And it's just going to be -4 over square root of 69i plus 7 over square root of 69j plus 2 over square root of 69k. And what are my units? Well, what are the units of the top? Inches. What are the units of the bottom? Inches. So what are my units of this unit vector? It's a unitless unit vector. That's exactly what we want. We took out the magnitude. We got rid of it. We threw it away. We said, hey, Mr. Position Vector, we really like your direction, but we're not so fond of your magnitude. So get out of here, magnitude. We want to throw our own magnitude on there. So now the next step is we say our force vector as a Cartesian vector is going to be equal to the magnitude that we want, which is F, the magnitude of that, times that direction, UAB. We divided out a magnitude, now we're multiplying one back in. We divided out the inches, we're multiplying in the newtons. Yeah, I'm going between unit systems, but hopefully you get the point. It could be newtons and meters. It could be feet and pounds. It doesn't matter as long as you're not mixing force with distance. So our Cartesian vector is then 20 newtons times -4 over square root of 69 I plus 20 newtons times 7 over square root of 69 J plus 20 newtons times 2 over square root of 69 K. Okay, this is a really powerful tool. Anytime we have a position vector that shares the direction with a force vector, we can very quickly find that force vector. I didn't have to draw a triangle and use my trigonometry because I had a position vector along that way. So let's jump into a practice problem. Determine the magnitude and coordinate direction angles of the resultant force acting at point A. So we're supposed to find the magnitude of the resultant force, which we call FR, alpha, beta, and gamma. Okay, so on the last problems, they gave you a drawing of a plane and some angles, and that's how you're able to find the components. What does this give you? Distances and dimensions, exactly. Okay, some people are way ahead of me, some people are behind me. I want to bring us all back together really quickly and just talk about what is up here so far. So far, the only thing I've done is I found RAB, which I found right here. Now, there was some discussion about how we find RAB. Visualization or RB minus RA? Visualization. Okay, that's how I did it too. But RB minus RA will also work, right? So if you were to find RA and RB and subtract RA from RB, that'll give it to you mathematically. So if you're ever having trouble visualizing, maybe do it both ways and see if they match. Okay? Okay, so looking at it, if I'm walking from A to B, I have to go along that green line, which I solve for right here to be 3 cosine 60. Then I have to go along the purple line in the y direction, which is 1.5 plus 3 sine 60. And then I go down 4. That's my position vector. Then I found the magnitude and divided by it. Why did I do that? Perfect. We're turning into a unit vector. We're getting rid of those meters. Throwing the meters out, saying I just want the direction, not the magnitude. Now I have a unit vector. What's going to be my next step? Multiply it by F1. Very good. So now what I need to find is I need to find F1 as a Cartesian vector. F1 as a Cartesian vector is just going to be F1 as a magnitude times UAB. Okay, if you have F1, that's the F1 that I got. It's written on the bottom here. That's F1 in newtons, full Cartesian vector notation. I kept a lot of units because I don't want round-off error, right? If you're doing it on your calculator, just keep it in your calculator and only write down as many to remind you what value it is in your calculator. If you don't know how to store a calculator as a variable, please come see me during study group or office hours. I'll show you how to do that because that's very helpful. Okay, so I got my F1. What's my next step? Find F2. And we do it the exact same way. We find RAC, then the unit vector in the AC direction, then we multiply it by the magnitude of F2. Okay, let's get back to it. I tried to write this big, so I didn't put all of the work out, but I wanted to make sure you guys could see it. So once you find F1 and F2, all of that work that we put into that was just to find F1 and F2. After that, it's the easy part. F1 plus F2 equals FR. You add the I's, you add the J's, you add the K's, you get your FR. Then you find the magnitude. There's one more step. What do I need to do now? Angles, coordinate direction angles. And do I need to draw some pictures of those, or how do I find those? We have an equation, right? So what's the equation for alpha? Cosine of alpha equals FRX over FR. Very good. So we can solve for alpha pretty easy. It's equal to the inverse cosine of the x component of FR, which is 157.4124, over its magnitude, which is 315.7786. They're both in newtons. It's good the newtons cancel out because you can't have an angle with, or you can't take the inverse cosine of something with units on it. Solve for that, and alpha ends up being 60.1 degrees. Cosine of beta is FRY over FR. So beta equals inverse cosine of 83.9 over 315.8. And I end up with 74.6 degrees cosine of gamma. Okay, don't forget the negative sign on the last one. You need to include the negatives in order to get the right answer down here, because the z component is negative. And of course, on my work, I would box all of the answers.